Welcome to Industrial PLC Applications. This video is PLC Programming Fundamentals, Part 1, Programmable Logic Controllers I/O or Inputs and Outputs. This video is part of a series of videos on PLC basic operation. After completing this video, you should be able to explain basic PLC operational purposes, explain the various input types a PLC uses, explain the various output types a PLC uses. PLCs, or Programmable Logic Controllers, are very simple 32-bit controlling processors that by today's computer standards may seem outdated and useless. They have very small memory capabilities, measured in kilobytes. They have slower clock speeds than any laptop and no video display. They have limited communication capabilities with no Wi-Fi or Bluetooth. Furthermore, they don't surf the net or play games or read email. But on the upside, they don't have random system upgrades or driver conflicts. So why are they so important to business? Because it's their simplicity that makes them so valuable to industry. They're simple to program, simple to monitor, simple to troubleshoot and fix. What they do is control automation and equipment reliably and predictably, repeatedly and efficiently, and safely for years, even decades. A PLC's primary purpose is to examine inputs, resolve very simple logic, and energize or de-energize outputs in response to the conditions of the inputs and the flow of the logic. The PLC used in this video series is considered to be a micro PLC, a class of PLC sometimes called a brick PLC. These PLCs have limited I/O and scalability and normally have a simplified or reduced instruction set. They're primarily intended for use in a single machine application. The processor on this model Allen Bradley PLC is placed between the 120 volt AC to 24 volt DC power supply and the small expandable I/O chassis. The processor communicates with the fixed I/O and expansion modules via the micro backplane within the I/O chassis. The number of discrete I/O, or inputs and outputs, is fixed on this model at 14 inputs and 10 outputs within the host processor unit, but can be expanded via the chassis and extension cards, which is beyond the scope of this introduction. So let's take a look at our inputs and outputs. Let's begin with our inputs. Inputs are devices or signals that originate outside of the PLC. They can be switches or data streams or even data from another PLC or computer. Some PLCs have input receiving hardware built into them, like the Micro 850 series, but the actual device triggering an input will be external. Furthermore, many PLCs can monitor thousands of inputs by communicating with remote input modules. Remember, the PLC reads inputs. Let's dive a little bit deeper into inputs. Inputs come in a wide variety of types and sources. They can be digital or discrete, analog, digital data, or system inputs. So what do we mean by digital or discrete inputs? Well, a digital or discrete input is an input that has only two distinct states of operation, off or on. Discrete I/O is the most common form of control for the PLC. Discrete inputs either sends or does not send a signal to the PLC. They are represented by a single digit, 1 or 0, hence the term digital I/O. Analog inputs, however, are inputs that change frequently and are seldom at the same value. With DC analog signals, the signal will always be more or less positive, that is, changes in amplitude or strength. With AC inputs, the polarity, positive or negative, can change as well as the amplitude. Here, we're looking at frequency. Most control analog signals are designed, however, for DC signal sources. Digital data inputs come from other sources. Although limited in host capabilities, the Micro 850 can be connected to a wide variety of external I/O which may send signals that contain data, such as the current speed of a motor from a VFD, the fault status of a remote I/O chassis, or the value being inputted into a human-machine interface or HMI panel view. Digital data can also come from another PLC. System inputs are generated by the PLC and are used to troubleshoot faults or slow processing speed, etc. They can also contain things like a real-time clock data that can be used to trigger specific events to occur. For example, turning on a flush cycle every Saturday during a non-production day, except on leap years or some other condition. Let's take a look at something called syncing inputs. Most PLC inputs are syncing inputs. This means the input signal voltage the PLC will interpret comes from the input device. Looking at the wiring diagram, the 24 volts DC goes out to the remote device. When the device's contacts are closed, the voltage is passed on or sunk to the input terminal. The PLC sees the presence of the voltage as a signal. Let's take a quick look at how an input appears in a program. In the logic itself, inputs are traditionally located to the left of and ahead of any input instruction. On the Micro 850, the host inputs are assigned a unique identification _IO_EM_DI_ the number of the actual input. Breaking that down, it's actually quite simple. IO for input or output, EM stands for embedded, DI stands for digital input, and then the last two characters after the underscore is the actual identification for the particular bit we're looking at. Now let's take a look at the other side of I/O, the outputs. Outputs, as far as the PLC is concerned, are signals sent to external devices with the intent to control an automated process. These can be anything from a simple binary trigger to turn something on or off, or streams of analog or process data to another PLC or a computer. Outputs are quite different than inputs. They're known as sourcing outputs. Outputs are sourced from the PLC. When the logic ahead of the output is true, the PLC will energize a transistor, a triac, or a solid-state relay to power the real-world output with 24 volts DC. Keep in mind, larger output loads must be done through relays. In the logic itself, outputs are traditionally located to the right of and at the end of all the inputs, conditions, and other instructions. On the Micro 850, the host outputs are pre-named as _IO_EM_DO_XX, or bit number. And that stands again for input or output, embedded, digital output, and the number of the output itself. The term output can take on other meanings, and here we should start thinking about other outputs. There are outputs that are a result of the execution of a particular instruction. Many other types of instructions are also considered as outputs or internal write instructions, or have an output associated with them. These can be things like timers, counters, data moving instructions, mathematical instructions, or logical decision instructions. Alright, this is the Allen Bradley Micro 850 family of micro PLCs. It's technically not a brick, although it's pretty close to it. A brick would be fixed and unexpandable. There is, within the Micro 850 family, a different side of core sizes, but there is also some expandability. So let's just kind of look at each of these different components. Starting from the left, we have our power supply. So this is a 24 volt output with 120 volt input. It has a self-check function on it, and notice they give you two provisions for the positive and two provisions for the negative. The next is the actual processor itself. That's the brains of the operation that's going to be analyzing the logic and solving it. It has three different communication ports available to it. It has an Ethernet port, a serial port, and also a USB port. Underneath is a very, very tiny switch called the Run Remote Program switch. Each of these different switch positions will cause the PLC to behave differently, and your access and availability to do programming will be enhanced or restricted based on the position of the switch. On the top, we have the inputs. When an input changes of state, the LED itself will turn off. So I've taken a normally closed push button, and when I press it, you can see that the normally closed contacts open, and it's no longer recognized by the PLC as being true. The other one is the number 9. If I switch it, it can be off, and I have this on a selector switch, so between 8 and 9 they're alternating between them. The next part we want to focus on are these. Obviously the power tells us that we're the power is being accepted and is activated. The run means the program that is in the memory is currently running. If I were to take this switch and put it into program mode, you can see that the run light is turned off, and any output that was controlled down on the bottom here, these are our outputs, will be shut off as well. When I go back into run mode, which is all the way over to the left, the outputs will turn on, and in remote mode, which is in between, remote mode allows you to run the program but at the same time make changes to the program. And again, my inputs are still operating. And depending on the button that I press, different activities will happen. To the right of the processor, you have a variety of expansion module capabilities. The trainer that's currently in use has an IF2 card, which is an analog input. It has an OF2 card, which is an analog output, and it has a isolated relay module. We're going to get into how these modules work much later. And on the end, it also has an I4RT2, which is a module for temperature, looking for RTDs and thermocouples. Now I want to point out something about these particular inputs on our terminal screws and our outputs on the bottom here. So most PLCs and most I/O are set up such that they are either what they call syncing or sourcing. And the easiest way to think of syncing and sourcing is where is the power coming from and how am I controlling it? So when you're looking at a syncing input, the power comes from the power supply, it goes out to an actual device, and then as the device changes state on or off, it comes back and is seen at the terminal screw. So the completed circuit then is from the common connector on the other side of it. So basically, if you want to think of it like a single light switch with a light bulb attached to a regular house panel, so the input acts the same way as the light switch. The light bulb is the PLC. So the light bulb turns on, the PLC recognizes that the switch has changed state and that there's power coming through to the input. Sourcing, on the other hand, is like looking at what happens after that light switch and a light bulb's been turned on. So you can think of it sort of like monitoring the connection between the PLC and the neutral or line 2, and something that you've put in between it, so that the PLC becomes the source of the current or voltage going to the device, whereas the inputs, we have the voltage made at the power supply, but the device itself syncs the 24 volts and presents that to the PLC. So the PLC is looking at the raw power coming in via the switch or a device that is sunk by the device itself. Could be a proximity switch, a limit switch, whatever. So that's the basic tour of the actual processor itself. In the next video of this series, we're going to look at programmable logic controllers. But in this case, we're going to look at logic flow and some programming rules that must be followed.